First, let's look at the relationship between temperature and capacity. So here we have a mass of air, and these blue spheres represent water molecules. This mass of air is completely full, so it has reached its capacity for water vapor and is at what we call the saturation point. Now, the relationship between temperature and capacity is that as temperature decreases, capacity also decreases. This means that if we take a mass of air that's at the saturation point and we reduce its temperature, we reduce its capacity, meaning that there's an excess of water vapor that the air mass can no longer hold. What this results in is this excess water vapor will condense and either form dew on the ground or will form clouds up in the atmosphere. Now let's look at the relationship between pressure and temperature, indicated here by the ideal gas law. So here we have a mass of air that has a set amount of water vapor. Now, if we increase the volume, we actually will reduce the pressure. When we reduce the pressure and the molecules spread out, this results in a decrease in temperature. And again, remember, a decrease in temperature will also decrease the capacity of the air. And when this occurs, this is called adiabatic cooling. When the opposite occurs and we increase pressure and increase temperature, that is called adiabatic warming. And both of these have major implications on air currents. Now let's look at latent heat. So here we have a graph that shows the relationship between temperature and energy or heat. So as we add energy, the temperature of a material, in this case we're going to talk about water, will increase up until the point at which it reaches a phase change. In this case we're going to have the melting point. At this point we can continue to add energy, but the temperature will not increase. And this is called latent heat. It's called latent heat because, again, we're adding heat, but it is not being converted into a change in temperature. So what's happening here is that we have ice in the solid form, and these molecules have bonds between them. When we add energy to this system, this energy is not going into raising the kinetic energy of the molecules, but it is going into breaking these bonds and changing this from a solid into a liquid. Now you will notice that when this phase change occurred, the molecules actually came closer together. And this just kind of shows one of the unique qualities of water, which is that its solid form is actually less dense than its liquid form, which again is why ice floats. So once that phase change has occurred, as we add more energy to the system, the temperature will again increase up until we reach the next phase change, which would be the boiling point. And then again, as we add energy to overcome the interactions between the molecules and allow the phase change to happen, so again, we're adding latent heat, there will be no temperature increase until that phase change has occurred, at which point an additional input of energy will result in an increase in temperature. So the way to look at this is if we're going from liquid to gas, so the phase change of evaporation, we are absorbing heat in order to break the interactions between those molecules. If, on the other hand, like say when a cloud is forming, we're going from a gas to a liquid, there's actually going to be a release of heat. And in both cases, this is latent heat.